Hi everybody, Physics Ninja here. Today we're going to look at simple harmonic motion. I've got a great review problem set for you. We have 10 problems, 31 questions dealing with everything that has to do with simple harmonic motion. So I got spring and mass, I've got simple pendulum, we're looking at frequency, equations of motion, acceleration, period, energy. There's a lot of graphs to analyze in this problem set. Okay, so this is what I suggest you do. Step one is you go download the problem set. So go in the description of this video. There will be a link there that will take you to a PDF. Second, you have to try out the problems for yourself. If you simply watch the video, you will have learned nothing. So first try the problems, then come watch the video and compare your solution to mine. All right, like with all my videos, if you like it, give it a thumbs up. Consider subscribing to Physics Ninja. It is a great way to support what I do. You can also give a super thanks if you can. And one other thing, now I have launched my t-shirt store. Visit physicsninja.etsy.com. Get a t-shirt if you want to support me in this way. All right, let's get started. Alright, here's problem one. A match attached to a spring with spring constant K is 2 newtons per meter is oscillating along the x-axis. Its velocity at time t reads this. What is the maximum acceleration of that oscillating mass? Alright, so if you're given velocity versus time, well, you should know that the acceleration versus time is simply found by taking the derivative of this function right here. So if I take the derivative of a cosine, I should get a negative sign that pops out. I'm still going to have that amplitude of 3.5. I will have a 2.2 that comes out, and this becomes sine of 2.2 multiplied by time. That is the acceleration for any time. Now what they are asking you for here is the maximum acceleration. And that maximum acceleration is simply the magnitude of this. So this number here is actually the maximum acceleration. It's simply 3.5 multiplied by 2.2. Put those numbers in the calculator and you should get 7.7 meters per second squared. And that there corresponds to choice B. All right, let's look at the next one. An ideal horizontal spring on a frictionless table is fixed at one end. The other end, we got a mass m. When a horizontal force is applied to that mass, it is displaced a distance d from its equilibrium position. Then you turn off that force. What is the maximum speed of this mass? All right, so for this one, I think what I would do is I would probably consider maybe some energy balance, okay? Because when I release it, I am going to have the maximum amount of spring potential energy. And that spring potential energy is going to be Ka squared. Okay. Now what else? Well, I know that once it passes through this equilibrium position, this zero position, all of that spring potential energy is going to be converted into kinetic energy. And this is how we're going to find that maximum speed. Now, if you just rearrange this, you can see that all of the choices here, they involve this quantity v squared. And that is simply the v squared that we have over here. So let's do a little bit of algebra. Just bring the mass on the other side. And let's see what we're left with. We're left with v max squared equals 2k over m a squared. Now, if I look at these choices, none of those choices look like this one over here. Well, that's because they all involve the force F. So one thing we have to realize here is if I'm applying some force F, and right at the point when I release it, that force has to be equal to the spring force. And the spring force at that point is given by Hooke's law. It's given by the spring constant K and multiplied by the amplitude. And the spring force is clearly toward the origin. So one thing I could do here with this expression is if I take 1A and I group it with that K, I can simply write that down as the force. You're still going to be left with one amplitude because it's squared here. And here you're going to have the force and now divided by the mass, okay? And that there corresponds to choice C as being the correct answer. All right, number 9 says a pendulum made of an ideal string of length L and a mass m is hung from the ceiling. It undergoes very small oscillations with angular amplitude and a period p. So they use the letter p here. M, L, and H are all doubled. What is the new period of this oscillation? All right, well, in your class, I am sure you talked about the period of oscillation of a simple pendulum. If that angle is small, that result looks like this. Now you got to be a little bit careful. Make sure you get these variables here in the right order. Again, you're looking at a system here where we have a simple pendulum. The pendulum here, the string has a length L and we have a mass M that is attached to it. And it'll simply oscillate back and forth. The period is how much time it takes to do one oscillation. We notice here that it depends on L and it depends on the acceleration due to gravity. It actually does not depend on mass and it doesn't depend on theta if that angle is small. And here we've said it's very small oscillations. All right, now we're going to double everything. So what is the new period? Well, we don't change the 2 pi. All we do now is we double the length. So that numerator here under the square root becomes 2L and we don't change little g. So right here, if I factor out a root 2, I'm left with root 2 and I'm left with everything else. I'm left with root 2 times the period. So you can see that root 2 is approximately 1.4. Therefore, D here is the correct answer for the new period. The new period is going to be bigger because the length increases and the length appears in the numerator here of this square root term. Good problem. All right, here's problem 2. We have a mass M. It's hanging from a vertical spring that has a spring constant K of 20 newtons per meter near the surface of the Earth. In equilibrium, the spring is stretched by 10 centimeters here, as shown over here in this second figure, relative to its relaxed length of the spring. The spring is then compressed by 1, shown in this most right figure over here, relative to that equilibrium position, and it's released into oscillation at time 0. The height of the object relative to the equilibrium height oscillates as shown below as a function of time. So this is what the height looks relative to that equilibrium position. So you can see right here, we started at +1. And basically what they're plotting here is that vertical position of that mass. All right, let's look at the first question. It says, among the 3 points, A, B, and C, when is the speed of the object the greatest? So when is the speed of this object the greatest if I started out at the top? So there's many ways to look at this. One thing you should remember is the speed is always the biggest when it goes through the equilibrium. And that corresponds to this point right here. And that looks like point A to me. Okay, so that's just something to know about simple harmonic motion. Another thing you can think about is, well, the speed is simply the magnitude of the velocity. And how do you get the velocity if you're given a position versus time? It corresponds to the slope of that graph. So they're really asking you, where is the slope the biggest? So if I draw like a mini slope right here, you can see although I get a negative number, they are asking me for the speed. So I'm really only interested in the magnitude of that value. Over here, the slope is 0, and over here, the slope is 0. It's simply a flat line. So the object's actually momentarily at rest there. So this here looks like choice A as being the best answer. All right, next question says, between the 2 time points marked A and B, when is the acceleration of the object the biggest? All right, so now let's just clean this figure up a little bit and let's think about the acceleration. Acceleration for a simple harmonic oscillator, again, if you knew the velocity, you can then take the slope of the velocity to find the acceleration. But one thing to remember is whenever the acceleration is big is when the force is a biggest value. So when do you think you're going to get the maximum force? You're going to get that maximum force when you are stretching it out the most, right? When the spring is stretched the most, that's when you are going to get the biggest force. And clearly at this point, there is no spring force because there is no amount of additional stretching. You get additional stretching right here at point B. So point B corresponds to the case where the acceleration is the largest. All right, so here's the continuance of problem 2. They say, what is the mass of the object? Here I've just cut and pasted that original graph. That spring constant we know. And one thing we know is that that spring stretched 10 centimeters when it was simply hanging there, right? So what did we have? We have mg before it began to oscillate, and we had something like this, right? And this was this original 10 centimeter stretch, but the object was in equilibrium here. So guess what? Well, that means that those forces have to be equal and opposite. So we simply set them equal to each other, and now you divide through by little g, and you get ky divided by little g. Go ahead and substitute. We get 20 for my spring constant. That initial stretch of that spring was 10 centimeters, so 0.1, and now divided by 9.8. I put those numbers in the calculator, and I think I got something like 0.204 kilograms. Okay, and that there looks like C is probably the best answer. All right, the next question says, which of the following curves would best describe the height versus time if the mass of the object was quadrupled and all other quantities remain the same? Okay, well, one thing we have to remember about a simple harmonic motion, a spring and mass system, is that the period here looks something like this, right? It's 2 pi divided, now be careful, make sure you get the order here, it's mass divided by that spring constant. That's the period of oscillation. Now, if we look at this graph up above, the time for one oscillation is this time right here. So this corresponds to approximately 0.6 from the time above on that graph. Now, what happens if we quadruple the mass? So what is our new period of oscillation? So I would do this. I keep the same spring the same. And what else? This mass here becomes 4m. Now, in that 4, I could take 2 out of the square root. So I multiply 2 by that original function here, okay? So my new period should be approximately 1.2 seconds. So now let's look at the graphs and see which of those graphs has a period of 1.2 seconds. That's the time for one oscillation. Look at choice B right here, right? It takes about 1.2 seconds to come back to where it started. So I think B here represents the best choice. It's still going to oscillate between 1 and -1, and all of those graphs show that. The only thing that changes here is the period of oscillation. All right, so kind of a nice problem. Here's problem 3. A pendulum hanging from the ceiling of an elevator is swinging with a period of 2 seconds when the elevator is at rest. Assume that the elevator is near the surface of the earth. Suddenly the elevator undergoes vertical acceleration and the period then increases to 2.2 seconds. What is the direction of the acceleration? All right, well, let's kind of think about both of these systems. So here's a simple pendulum just on earth, and we're told over here it takes 2 seconds. That is the period. T is 2. All right, now I'm going to take that same pendulum here, and I am going to mount that entire thing inside an elevator. Okay, and now the elevator is either accelerating up or down. So how would we figure that out? Okay, so one thing that we should do is let's remember how you calculate the period of oscillation for a simple pendulum. The period, at least when it's on Earth at rest, it looks something like this. It's the length divided by little g, right? And in this case, we know this value here is 2 seconds. So you could actually use this equation to calculate the length of that string right here. Because we know little g on Earth is 9.8. Now, let's think about the elevator situation. What would be modified here if we're going in an elevator? Okay, for the elevator, basically my period here, I don't change the 2 pi. I also do not change the length of that pendulum. That stays the exact same. The thing that I'm changing is basically this effective little g right here. It's kind of a similar problem that if you're just going up or down in an elevator, that your weight is going to seem different, right? If I'm standing on a scale and I'm accelerating upward, I know that my weight is going to seem heavier, right? It almost appears as though the little g, the effective little g, is a little bit bigger, right? And in the case when I'm accelerating down, the weight that I would measure in that case would be m multiplied by g minus a. That would be my weight in this case. So this here appears like the gravity is a little bit less. We might call this an effective little g. All right, so this is kind of what's going on here. If my period now is going to be 2.2 seconds, well, guess what that means? That means that this effective little g has to get smaller, okay? And the question is, by how much does it get smaller, okay? Well, we simply have to replace this effective little g by the acceleration due to gravity, little g, and minus the acceleration. We know it has to accelerate down, okay? So I want to make this little g a little bit smaller, because if I divide by a smaller number, I am going to get a larger period. So right away, I think we can answer that it has to be accelerating downward, okay? Now, what else would we have? What's the magnitude now of this acceleration? Well, guess what? We simply have to solve this equation right here. Now, let's be a little bit careful because we really need this length in order to solve for what the acceleration a is right here. So the length you can get from our first expression, okay? So let's go ahead and first solve for that. So I'm going to bring the 2 pi down at the bottom, and then I have to square everything. So my length expression should look like this. It's the 2-second period divided by 2 pi. Then I have to square everything and multiply it by little g, which is 9.8. Okay, if I go ahead and put those numbers in my calculator, we get 1 divided by pi. Let me find my pi. Okay, I have to square that. And now times 9.8. All right, I get approximately a length of 0.99, basically 1 meter. All right, now we're going to go ahead and solve this other problem. My goal now is to solve for this acceleration a. So let's bring the 2 pi on the other side. So we're going to get 2.2 divided by 2 pi. I have to square that to eliminate that square root term. I have my length L, and now I have G minus A. Okay, so now we have to do a little bit more algebra. I'm going to bring the G minus A on the other side, and now this whole term here is going to be a 0.99, that's the length, now divided by this whole fraction here. Let me just leave it like this, 2.2 divided by 2 pi squared. All right, at the end I can write down that the acceleration A is going to be 9.8, and now it's going to be minus this entire term here. So this is my 0.99, 2.2 over 2 pi, and I have to square that bit. All right, now this is not the most elegant solution, so let me just go ahead and write the acceleration here. Let me punch those numbers in the calculator and see what I get. So 0.99 divided by this entire big fraction here. So this is 2.2 divided by 2 divided by pi, and I have to square that thing. Okay, I get 8.07 just for this term right here. Okay, this here was 8.07. That is actually an acceleration term. Okay, and now you go ahead and simply do 9.8 minus that number. So here I go in the calculator, and I should get a value that is approximately 1.7 meters per second squared. Okay, so that's kind of a little bit of a more difficult problem right here, I think. Okay, this is not a standard pendulum problem because here we are in a frame of reference that is referred to as a non-inertial frame of reference. All right, let's go to the next problem. Here's problem 4 in an experiment in a lab shown in the figure. You study the motion of a mass M hanging from a vertical spring with spring constant K. It was initially in its equilibrium position. It was then lifted up by some small distance. If afterwards starts to oscillate vertically, assuming that the period of oscillation is t, the frequency of the oscillation is f, which of the following individual potential energy and kinetic energy versus time graphs is correct? All right, so let's go back and just read this because you lift it up a small distance and then it's released, okay? That word means that that initial velocity should be 0. So at time equals to 0, I better have that the velocity is 0. Now, there's no mention of velocity here, but they do talk about kinetic energy, right? These are the kinetic energy graphs, and you should remember that kinetic energy is calculated by 1/2 mv squared. If at time 0 my speed is 0, it means the kinetic energy must also be 0. So let's have a look at this one. Look at that graph over there is wrong. It starts at the kinetic energy of 2, but that cannot be correct, okay? Now these two over here, A and B, you are correct because look at, we both start here at 0 kinetic energy, so we're fine with those ones. The next thing we have to do now is you have to look at the potential energy graphs, the 3 graphs below it. Again, we don't need to worry about this one. One of them starts over here at a maximum value, and one over here starts at a medium value, right? Half the maximum value. Again, if you're going to lift it up, what's going to happen here is if I plot the position here versus time, if I start at some position over here, again, it's simply going to oscillate up and down between both of those. That potential energy is simply written as 1/2 K multiplied by that amount of stretching or compression squared. Okay, so it should be a maximum value. It's never going to go beyond these points here, beyond that maximum and beyond that minimum value. So really this here is the best choice, okay? When the kinetic energy is 0, you should have a maximum potential energy and so forth, okay? All right, so I think A is the best choice for this problem. Let's go to the next one. Problem 5 says a block of mass of 15 kilograms is resting on a horizontal frictionless surface and attached to a spring with a spring force K of 370 newtons per meter. A force F is applied to the block in the positive x direction where we compress it by 0.2 meters. What is the magnitude of that force F? Okay, the magnitude is given by Hooke's law right here, right? This is simply the spring constant multiplied by how much did we compress that spring right here. So this is just a straightforward calculation. The spring constant is given as 370 and the amount of compression that we have is 0.2 meters. Put those numbers in the calculator. You should get 74 newtons is this applied force. C is the correct answer. Okay, so the next question says the force is removed and the block starts to oscillate. How long does it take to complete one oscillation? By definition, that is what we refer to as the period of oscillation. And I'm going to use the letter T for that. For a spring and mass system, look on your formula sheet. Now make sure you get those letters in the right order. It's m/k for the period. So now we simply know everything. You have to put the numbers in the calculator and plug and chug. This is 15 and divided by that spring constant of 370. All right, put everything in the calculator here, and I think I got something like 1.26 seconds. That looks like choice A to me. Okay, not too bad. Next problem says, what is the speed of the block when it reaches its equilibrium the first time? All right, so what do? We start off with a whole bunch of potential energy, 1/2 Ka squared. And once you go through the equilibrium position, there is no more spring potential energy. You've converted all of that energy into kinetic energy. So that's it, that's all. What we want to do here is you want to find what that speed is, and it's actually the maximum speed you're going to have. Bring the m on the other side and take the square root of the whole thing. Your expression, algebraic expression, should look like this. Once I take the square root, I am going to have simply a, that amplitude, that 0.2 meters that I started out with. So let's just go ahead and substitute everything in here. We get 370 for the spring constant over 15, and this number over here is 0.2. I put everything in the calculator here, and I think I got 0.99 meters per second. That there corresponds to choice C. We are off and running. Let's go to problem 6. All right, problem 6 says a block is sitting on a horizontal frictionless surface, again, attached to a massless spring, in its equilibrium length, a force F is applied. So it's similar to the previous problem we just did, okay? Determine the magnitude of this force F. That is just given by the magnitude of that spring force, which is Kx. Simply different numbers. So this is a pretty straightforward problem, 0.1. So that there looks like 21 newtons. I don't even need a calculator for that one. Let's go ahead. Choice E is the correct answer, period. Well, we already know the expression. We've just done this problem. So nothing new here. Again, it's m/k, 2 pi. The mass in this problem was 6 kilograms over 210. Put that in the calculator. I should get something around 1.1 seconds. And that looks like choice C to me. All right, the next problem, or next question is a new one. If the applied force F is double to 2F, the oscillation period, what? Does the period increase, decrease, or stay the same? So what happens if I apply twice the force? If F gets changed to 2F, well, my amplitude, right, the amount that you're going to compress this spring is going to increase. My amount X is going to change to 2X. But they are asking me what? They're asking me something about the period T. And look at my expression for the period T. It's right here. It depends on 2 pi. That is not going to change. I don't change the mass, and I'm not changing the type of spring. So this is actually a really, really important point, is that the tension, it doesn't depend on the amplitude, okay? It doesn't matter what you do to the amplitude. Tension doesn't depend on A, the amount of stretching or compressing. So that means that everything here has to stay the same. That means C is the correct answer. All right, here's problem 7. A simple harmonic oscillator has an angular frequency of pi over 3 radians per second. The mass is 100 grams. The mass started off with a position extended from the equilibrium at x equals to 0 by 15 centimeters with an inward velocity of negative 10 centimeters per second. All right, first question says, what is the distance of the mass from the equilibrium position at time equals to 10 seconds? All right, this is probably one of the hardest problems on this problem set, but let's just start off by writing an equation of motion that tells you the position of this harmonic oscillator, okay? I can write it as something like this: an amplitude multiplied by cos of omega t. Now, this other term here, you also need to have this additional term here because at time equals to 0, the object is actually moving, okay? So this is a very, very important thing. So what do we know so far? We know that omega is pi over 3, so that's important. What else? Once you know the position, you can also write an expression for the velocity at every single time. You have to differentiate this with respect to time, and you're going to get this value here, minus omega times a, and then this becomes a sine of omega t plus phi. Okay, again, you know the omega, but there are two things we don't know right now. We don't know what the amplitude of the motion is, and we also don't know what this phi is, and that's going to be related to the initial conditions of this problem. So let's write those down. So for example, at t equals to 0 seconds, well, what is the position of the object? Let's substitute t equals to 0, and what do you get here? You get a multiplied by cos, and that omega times 0 goes away, but you're still left with that angle phi. So that is my initial position, and guess what? We know what the initial position of this object is. It's 15 centimeters. Okay, but I still have two unknowns, so I need two equations to solve this. The next thing I have is, what is the initial velocity? What is the velocity of this mass at time equals to 0? For that, you have to substitute into the second equation. And here we get minus omega times a sine of this angle phi. Okay, so I now have two equations, and guess what? We have two unknowns, so we should be able to solve this. What I'm going to do is I'm going to label this equation 1 and equation 2, and in order to get rid of the amplitude, what I'm going to do is I'm going to do equation 2 divided by equation 1. Okay? If I do that, I am going to get rid of the amplitude. And if I do 2 over 1, I am going to get what is the initial velocity at time 0 divided by the initial position at time 0. And now this other term here is going to be left with minus omega. And since I did 2 divided by 1, I am going to be left with sine divided by cosine, and that is tangent of that angle phi. So this is an important equation because guess what? The only unknown in this equation right here is this angle phi. So what you have to do now is just bring the negative omega over to the other side, and then take arctangent in order to isolate what the angle phi is. So you should be able to write this down. Tan of minus 1. Now if I brought everything over to the other side, I should have that initial velocity, and here I should have negative omega times the position at time 0. So this is an important equation, and once I substitute all the numbers in here, again, I'm going to have tan minus 1 negative. Now what is my velocity? It's negative 10 centimeters per second. That is minus 0.1 meters per second. My omega here is pi over 3. So I have an extra negative in there. I don't know how that got in there. All right, and what else? The position at time 0, that position at time 0 is 15 centimeters. All right, now be careful when you do that in your calculator. Also, make sure your calculator is in radians here. Once I do this, I think I got 0.567, and that is in radians. Okay, so this is important because it's the term that gets put into the position and also into the velocity term. Now guess what? They're asking me for the distance the mass is from equilibrium at 10 seconds. So I have to substitute 10 seconds in here, but I still need to know what this is. So what you have to do now is you have to go back to either equation 1 or equation 2 and solve for that angle phi. So I'm going to use equation 1 right here, and I'm running out of room here, but we can isolate that amplitude now. So that amplitude is simply going to be what is the initial position divided by cosine of this angle phi that I just solved for. We substitute the numbers in here, so that initial position is 15 centimeters, and then we get cosine of 0.567. Again, everything in radians. Now we're going to get an amplitude here, which I got 0.178 meters. All right, now guess what? Now we are in a better position. So I am looking now for the position at 10 seconds. So now you could substitute in all the values here. 0.178 cosine of omega, which is pi over 3. The time now is 10 seconds, and I still need this additional term here, 0.567. All right, you put all of those numbers in your calculator, and guess what? I get a position of 0.0077, and that should everything be measured in meters. So that looks like choice E being the best answer. Question 11 says, what is the spring constant now? Well, remember, for a spring and mass, the angular frequency, angular frequency is related to the spring constant and to the mass by this relationship. If you square both sides, you're going to get an omega squared equals to k divided by m. So bring the mass on the other side, and now we have an expression for that spring constant. It's simply the mass of the object multiplied by the angular frequency squared. We can now substitute in what we have. So the mass, they said, was 100 grams. That is 0.1 kilograms. And my angular frequency, we're told, was pi over 3. I have to square that term. Put those numbers in your calculator, and you're going to get a spring constant of 0.11 newtons per meter. All right, and that there looks like choice D to me. All right, let's go to the next one. What is the amplitude of the oscillator? Well, guess what? I've actually already solved for the amplitude, and the questions kind of come in a weird order here, but the amplitude we've already solved for, that is the variable A that appears here in my equation of motion. All right, the last question for this problem says, what is the acceleration of the mass just after it was started, when it's at this position right here? Well, how would you find the acceleration for any time? What you have to do is you simply take the derivative of the velocity. That's the definition. We have an expression up there for that velocity. If I differentiate that, I'm going to get another omega that's going to come out. And then I'm going to switch back to a cosine of omega t plus phi. But look what happens right here. What is this value right here? A cosine of omega t, right? A cosine of omega t is the definition of the position. So all we have to do now is simply substitute minus omega squared multiplied by that position for any time. That is how the acceleration is related to the position. They're asking me now when the position is 15 centimeters. Well, again, you go in, substitute in all our values. We have our omega, which is pi over 3. You square that. And now my position is 0.15. Now, put those numbers in the calculator. You should get minus 0.16 meters per second squared as being that initial acceleration. And that there looks like it is choice C. Again, the negative sign is important here. It's telling me that it is accelerating toward the equilibrium position. All right, kind of a little bit of a harder problem this time, but hopefully you understand the solution. All right, here's problem 8, considerably easier than the previous problem. We have a block of mass m, 4.1, hanging from a spring with a spring constant of 31.5. The block is initially at rest. Okay, it's lifted a distance of 0.169 meters and released, after which it oscillates up and down. What's the angular frequency? The definition of the angular frequency, whether it's vertical or horizontal, is still given by the same value right here. Okay, so all we have to do now is simply substitute our spring constant, 31.5. The mass is in kilograms, 4.1. You put all those numbers in the calculator, you will get 2.7 radians per second. Okay, so that there looks like choice A to me. Next problem says, what is the maximum velocity? Okay, the maximum velocity, again, this is when you convert all of that kinetic energy, all of that spring potential energy, which is 1/2 Ka squared, and you convert all of that energy into kinetic energy. Okay, all we have to do now is solve for this speed, and this is when you're going to get the maximum value of the velocity. You notice you can write this here. If I bring the mass over to the other side, I get k over m. Now this is still squared over a squared. Now if I'm looking for isolating v, you just take the square root of both sides. That's k over m. And this here becomes a. Again, this plus or minus solution, but we were looking for just a positive solution here, basically the magnitude, although they asked for velocity. Yeah, you could just plot the magnitude, or calculate the magnitude rather. This is also omega times a. All right, and we just solve for omega, so this is pretty straightforward. 2.77 is my omega value, and the amplitude of this oscillation here is 0.169 meters. Okay, so we put those numbers in the calculator. You should get 0.468 meters per second. That is the max speed that you're going to get, corresponding to choice D. All right, what's next? Next one. The block is brought to rest. It is now lifted a distance. Okay, so it's lifted farther up this time and released. So what does this change here compared to the first one? Again, this changes the amplitude of the motion. So now they say compared it when it was raised this shorter distance and released, how does the angular frequency omega of the oscillation? Does it increase, does it remain the same, or does it decrease? The key to this one for simple harmonic motion is that the amplitude does not depend on the frequency, the frequency does not depend on the amplitude is a more accurate statement. So that means that the frequency of oscillation remains the same. For me to change the omega, I have to change the spring or I have to change the mass. That's the only way I can do it. Here's problem 9. A ball of mass m of 3.3 kg is hanging from a string of length 3.8 meters and oscillating as a pendulum. First question says the period t of oscillation. All right, so remember what we have here. If you have a pendulum here, this has a length L and this is the mass m. And it simply swings back and forth. The period of oscillation is given by this expression, 2 pi. Okay, make sure you get the order right here. It's L divided by little g. We know everything in this problem. The length is provided to us as 3.8 meters. Little g is 9.8. Okay, put those numbers in the calculator, and I think you get 3.91. That's measured in seconds. That there corresponds to choice D. All right, next problem says, if the length of the pendulum remains unchanged, but the mass of the ball is increased to 6.6, the period of oscillation, well, look at this problem again. If I want to change the period of oscillation, I have to change the length or I have to change the acceleration due to gravity somehow. If I change the mass of the ball, it does not matter. It has no effect on the period, okay? Because the mass ends up canceling out for a simple pendulum. It's a little bit different from a spring and mass, right? For a spring and mass system, if I change the mass, I will have an effect on the period, but not for the simple pendulum. This is an important point in this problem. All right, here's problem 10. A pendulum consists of a bob of mass 0.3 suspended by a massless string of length 7 meters from the ceiling. It performs small oscillations about its equilibrium position. What is the angular frequency of the oscillation omega? Well, the definition of omega here for a simple pendulum is G divided by L. Okay, well, this is pretty straightforward. This is 9.8, and this is divided by the length. And guess what? You put the numbers in the calculator right here. You should get something that is like 1.2 radians per second. All right, that there corresponds to choice C. All right, next problem says, if the length of the pendulum string is increased by a factor of 4, the angular frequency changes by what factor? All right, so my original angular frequency is given by this. And now my new angular frequency, if I make any changes, I do not change little g, but I change the length here by a factor of 4. So the length becomes 4L. Now think about it. That 4, I could take it out of the square root, and I can represent it by a factor of 1/2. And I'm still left with this expression, G over L. Well, G over L, the root of G over L is nothing more than that original frequency that I had. So my new angular frequency here becomes 1/2 multiplied by that initial angular frequency that I had. So it changes by a factor of 1/2, okay? It's going to be smaller. All right, let's go to the next one. On the surface of Jupiter, the acceleration due to gravity is 2.5 times that on the surface of the Earth. Compared to Earth, when the pendulum is taken to Jupiter, assuming that the string length stays fixed, what happens to the angular frequency? Again, pretty straightforward problem, because now we would take the little g on the surface of Jupiter rather than Earth. We're not going to use 9.8 here, but we've increased this factor. Okay, so omega then, if I don't change the length L, omega becomes proportional to little g. And since I'm increasing little g, I am also going to increase this value of omega. Okay, so increases. B is the correct answer for this problem. All right, let's go to the next one. All right, a mass of 0.5 kg attached to a massless spring is displaced from its equilibrium by a distance a, and then it's released to perform simple harmonic oscillations. The spring constant of the spring is 8 newtons per meter. What is the period? All right, so we've seen this equation many times. Now it's simply 2 pi. You go on the equation sheet and be careful that you get the order correct here. It's m over k for the period. All right, we simply substitute everything we have. The mass is 0.5. Our spring constant is 8. Put those numbers in the calculator. I think I got 1.6 seconds. That looks like choice A to me. All right, next question. If the total energy of the oscillation is 0.4 joules, what is its maximum displacement A? So if the total energy, well, we could examine when all of the spring or all of the energy is in the form of spring potential energy. That total energy then you can write as something like this, and I know what E total is. It's 0.4. The only thing we have to do here is isolate and solve for the amplitude. So bring the 2 upstairs. We get 2 times E total. Divide through by that spring constant, and then take the square root of everything, and you're going to get an expression for the amplitude. Now you're in a position to just substitute my numbers. So I get 2. The total energy is provided in the question, 0.4. The spring constant is 8. Put that in the calculator. You get an amplitude here of 0.32 meters as being the value of A. Okay, and that there corresponds to choice B. All right, our last problem, what is the maximum speed? The maximum speed is obtained when this total energy gets converted into kinetic energy, when you're flying by that equilibrium position. Again, this is a value we've seen before. We want to isolate for the speed v. So again, you take the m on the other side, and then you have to take the square root of the expression. So you're going to have this, and you still have one value of the amplitude. That's it. We can simply substitute all our values. So we have 8 now for the spring constant, 0.5 for this, and we've already solved for the amplitude, which was 32 meters. All right, put those numbers in the calculator, and we should get something to the order of 1.3 meters per second. And that there corresponds to choice A. All right, folks, hopefully you enjoyed this problem set, and hopefully it got you ready for your exam on simple harmonic motion. We'll see you next time.